right, let's get started. Sign sheet. Get that passed around. So, we're making great progress in here. First off, if you have not yet done so, y'all have a present for me. Homework number 1. That's due today. Homework number 2, assigned today. It's due on Friday, February 7th. I'll go ahead and tell you that in concrete design, we were sort of, I don't want to say booking it, but we really wanted to make sure we were knocking everything out. In here, we're making ample progress, so there's no reason to move this homework deadline. System's going to be, I know it's steel design, but I guess it's set in stone. It only works in concrete, so we affixed it, we welded it. I don't know.
We appreciate the effort.
Thank you. I try. I know that these jokes, y'all might reach your limits there. That was a really bad one. That looked really bad. Somebody had mentioned about not making it on Wednesday. Nobody's going to make it on Wednesday because we're not going to have class on Wednesday. I'm going to be in a plane at about 37,000 feet on Wednesday. So we won't have class on Wednesday. We will be back on Friday. On Friday, we will have a more in-depth discussion of shear lag and then finally get into some full-blown tension member analysis problems. And then once we finish tension member analysis, we can then say, okay, how do we design? And so the long and short of it is, tension member analysis is all about, here's a tension member, what is its capacity? How much can it hold up before it fails? The tension member design is, okay, here is a load, how do I select a tension member to adequately resist that load? And you can't do that if you don't understand its capacity. So that's sort of where we're at. I'll pull up the homework real quick near the end just to show you where we're at. You'll definitely be able to do the first problem after today and tackle a large chunk of the second and third problem after today. You probably won't be able to finish the second and third problem after today, but you'll see what I mean here in a little bit. Okay, so we're going to get back into section property computation, specifically gross and net area. So let me sort of backtrack. So last time we sort of began the discussion of, well, how do you define the capacity of a tension member? I've got a piece of steel, I'm yanking on it. How do I determine how much load that member can carry before it fails? Well, it's a function of what limit state you're looking at. So the yielding in the gross section, the fracture in the net section, and so on and so forth. But it's also a function of the member itself and its various section properties. Namely, if I cut a section through a member, we're using sigma equals P over A. Well, what's A? Well, it depends on if you're cutting through the gross section or through the net section. Now, the gross area is usually pretty straightforward. You either compute it or you look it up in your AISC 15th edition steel construction manual that everybody brought with them today, right? And then also, or you can compute it. That's the gross area. But the net area there's a little bit more nuance to it. First off, if you're dealing with parallel bolt pass, you have to recognize that your hole diameter is 1/8 of an inch larger than your bolt diameter because of various reasons that we've discussed. Either you have to drill it larger, and B, we eliminate that little bit of a lip of material around the hole analytically. But then there's also the discussion of staggered bolted connections. Remember, I'll go back a few slides. So we're always checking for a staggered connection along the lead line. So remember, the idea is that here's my tension member, and so the tension member, the main body, the gross section is all the way over here. So imagine if you took a rubber band and sort of stretched it along that member. The bolts that it hits, those are the lead line. So would this path fall on the lead line? Yeah, because the bolts remain intact. With this one, yeah, because all the bolts remain intact. With this one, again, yes, all the bolts remain intact. But with this one, no, because the front bolt is sheared off. So we're always going to limit our discussion to lead line paths. Okay? So far, so good? All right. Now, let's see. So here's our fundamental expression for the net area. This is a more general one that you could sort of, I guess, write down in your notes. I have a set of summary, like a summary of relevant formulas here in a little bit. But this is one that you could sort of hang your hat on. This is the net area formula. Gross area minus the area loss due to bolt holes plus any stagger factors. And we add the stagger factors because a diagonal path would have more area, so it increases the net area. And that's for bolted connections. For welded connections, as you know, you're not removing any material, and I'm sort of talking about fillet welded connections, the net area equals the gross area. And so with that, we've got our net area path shown. So we're going to look at the net area of this section. Okay, so we're going to look at this plate, which is, if you see here, this plate is 12 inches wide, and so that's this dimension, and you can add that up and see it's 12 inches, and it's 1 inch thick. Okay. Now, a couple of things that you might see here, for instance, this TYP. You notice that I didn't dimension all of these. I only have one of them because that's a typical dimension. So if you ever see a TYP abbreviation, that just stands for typical. So this dimension here, this 1.5 inches, is this the S dimension or the G dimension? I'm asking you. Tell me. See if you remember this.
What was G dimension again? I forgot.
It looks like it's for S dimensions.
Oh, snap.
Remember, S is parallel to the load, G perpendicular to the load. So that 1.5 inches, is that the S or the G?
Yes.
That's S, that's the stagger. So what is the G for these diagonal failure paths? I'm asking you. Exactly right, 3.5. So between bolt lines, that dimension is 3.5, that dimension is 1.5. Does that sound good? All right. All right. So I'm lazy. Every time. I'm actually going to stretch that out a bit so that it's a little easier reading. Oh my, that's a bit too much. That's good. Okay, so here's our problem. I'm actually going to move that down a bit. Example 3A. So before we start identifying failure paths and things like that, let's compute a few basic quantities. Let's talk about the gross area. What is the gross area of that plate? This is an easy one. That's pretty good. There. Anybody got it? Let's talk about, all right, so here's the plate. Okay, so let's make sure that we're clear on this. So here's the plate. And so it sort of goes like that. And so what we're seeing is sort of this thing. Right? And so if I looked up top, maybe the plate looks like this. And so here on the end, I've got this whole thing, or that whole thing. And then the main body of the member goes all the way out. Now the gross area, I'm talking about samurai sorting or lightsabering through just the main body. And so if I cut through that plate and I look at it, what is the area of that plate? I promise it's not a trick question.
Isn't it just 12?
12 what?
Inches squared?
Yeah, it's just 12 times 1. Yeah, it's pretty straightforward. Because the plate is 12 inches by 1 inch. So I promise, I'm not trying to trip you up on that. It's simple. Okay, is everybody okay with that? Okay, all right. Now, let's also look at the bolt holes. So the diameter of the bolts are what? What were they for this problem? 3/4. So the hole diameter is the diameter of the bolt plus 1/8. So that's 7/8. And so since that's 7/8, what we could also say if we wanted to make that a little even easier is the area of the hole is the diameter of the hole times the thickness. And we're afforded the opportunity just to compute a single hole area because all the hole areas are the same. They're all going through the same plate. If it was an I section or like a wide flange and you had bolts going through the flange and the web, well then you couldn't use the same quantity because they have different thicknesses, right? The web might have a different thickness than the flange, but because it's a single plate, they're all the same. And remember, it's the diameter times the thickness, right? Because if you cut here, like through that section, for instance, you're going to see this plate, but then that area is going to be removed. And the area of that is the diameter times the thickness, okay? So this is 7/8 times 1, and maybe just to add some, just to differentiate, this is 0.875 inches squared. Sound good? Now, last thing I want to go ahead and compute now is the stagger factor. This is new, okay? So in order to compute a stagger factor, that's this term here, S squared over 4G times the thickness. You need three things. You need the thickness. This is a 1-inch thick plate, so that's pretty easy, okay? And then you need your stagger and your gauge, okay? Now your stagger is parallel to the load. So the load is going this way. We're talking about this distance. Now whether you're talking about this diagonal path or that, this one or that one or any one of these, the S value is going to be 1.5 inches, okay? Is everybody okay with that? And then the G value, the gauge distance, again, between bolt lines. And so if we're talking about from here to here, we're talking about that or that or that or that. It doesn't really matter what path I'm talking about. Between bolt lines, so I keep using the term between bolt lines because I'm not talking about that distance. I'm talking about those. So 3.5. Okay? Now if I've got that, therefore our stagger factor is S squared T over 4G. And that comes out to what? We'll say 3 decimal places just to keep it consistent. We got a value for me?
0.161.
There we go. And what are the units?
Inches cubed.
Not in, because, well, look at the inches on the bottom. It's inches cubed on the top, but there's an inch on the bottom, so it's inches squared. And remember, the units have got to be consistent because you're ultimately taking an area and adding and subtracting these values. So if this is in square inches, that's going to be in square inches, and that's going to be in square inches. So everything's got to be consistent. All right. Everybody okay with this? All right. Okay. Now, this is the new part, okay? We have a net area problem, and because we have staggered connections, we have multiple potential paths that this section could fracture on, okay? So what this is going to be right now for us in here is an exercise in identifying those failure paths, okay? Now, one of the ways that we do this, just from a classroom perspective, so that we can all speak the same language, is we use some letters to denote the different paths that we're looking at. Now, remember, we're talking about the lead line. Now, pop quiz to see if everybody's paying attention. Am I talking about these bolts over here on the left, or am I talking about these bolts here on the right? What's the lead line? The ones on the left or the ones on the right? No, the left, the left. Because remember, we start out in the main body of the member, which is over here. That's what this break line is indicating to you. And imagine taking that big old rubber band, stretching it this way. Those are your lead line, okay? And the reason why that's not the case is because in some connection arrangements, you can get different paths this way than you can over here. So you got to make sure that you're identifying the right one. Is everybody okay with that? Again, this is, please, if you've got a question, this is important stuff. Yes, sir.
Back to what you just said. If you have two beams together or bolted, does that mean you have two lead lines, one on each end?
That's a great question. And what I'll say about that is the lead line for this plate up top
Would be this.
is this one. But for the one in the background is the one over here. That's a great point. All right, that's an excellent point. This is good stuff. Anybody else? This is good stuff. Okay. Now, what I'm going to do is I'm going to throw some terminology out, and I'm going to identify just a couple potential regions, and you all are going to help me identify some failure paths. So what we'll do is we'll say, okay, we'll call this maybe point A, call this point B, call this hole C, call this D, call this E, call this F, call this G. And so the reason why I'm doing that is because I'm going to draw a bunch of lines, if you will, identifying all of the potential ways that this could go. Like we could have maybe some stuff like this, that. A bunch of different diagonal lines indicating where this stuff could lay out. All right. Now, here's what I want you all to do. All right, let me move this over. Let's look at possible failure paths. Possible failure paths. I want somebody here to look at this terminology that I've thrown out at you. And let me be clear. For your homework, like the first problem I threw out the letters at you, or for the first problem I threw out the letters, the second problem and the third problem I did not. So you have to sort of identify this yourself. So I'm like easing you into it. All right. Somebody look at this terminology and identify a potential possible failure path. Just spit one out. We'll see if it works.
A to F.
A to F. So maybe I'll call that A, D, F. Okay? Now for that failure path, how many holes would I be subtracting? One. And how many stagger factors would I be adding? Goose egg. There's no diagonal pass along this one. Sound good? Okay. Somebody else give me another one.
A-D-E-G.
A-D-E-G. Exactly right. Now, analytically, that is different than ADF. Why? Because we have how many bolt holes that we're subtracting for this one? 2. And how many stagger factors? 1. Okay. Keep that in mind. Is there a path that's kind of like that one that we could also name? There's A, D, E, G. What about another one? There's one that's kind of like it.
BCDF.
B, C, D, F. Now, A, D, E, G. How many holes? 2? How many stagger factors? Now, the next one that you mentioned, B, C, D, F. How many holes? How many stagger factors? So are they really different paths? No. In fact, really they're the same. So I'm going to say they're basically the same path. Now, that is not always the case. Okay? Sometimes they wouldn't be the same. And a particular instance where they wouldn't be the same is if this distance is different than this one. And you're thinking, oh, come on, Dr. Mike, who the heck would do that? Well, there is a very specific example where that could happen here in a second that I'm about to show you. So don't worry, it can happen.
Would that 2.5 inch distance affect it as well if it was different?
What do you mean, if this was 2.5 and this was 3 or something?
Yeah.
That's a great question, and the answer would be no, because that's not distance between bolt lines. Because your diagonal path is defined by the 1.5 and the 3.5. So whether this is 2.5 or 76 really wouldn't matter. But if there was another bolt line down here, then yes, it would matter. That's a great question. So is everybody okay with that? That's a great point to make. Very good. Are there any more paths?
B, C, D, E, G.
B, C, D, E, G. How many bolt holes for that one? And how many stagger factors? 2. Great. Exactly right. Why didn't anybody mention that one? Why not that one?
It would break with bolts on the other side.
It would break that bolt, right? Bolt D would fracture. Okay? Can you check that path, like analytically? Yeah, you can. In no way, shape, or form am I going to expect you to, because it never goes, okay? And it's really more, I mean, it won't control, I promise you. I can show you how it works, but I'm not going to do that until down the road once we've sort of figured out what's going on. So far, so good? Okay. Now, once you've identified the possible failure paths, the rest of this becomes pretty easy. So watch this. All right? So don't forget we have a gross area of 12 square inches. We have a whole area of 0.875. And we have stagger factor of 0.161. Just remember those values. You don't have to rewrite them. I'm scrolling down, so I just wanted to have them off to the side. Okay. I'm going to draw myself a little table. Now remember, the net area formula is the gross area minus our whole areas plus our stagger factors. I don't need this. Okay? So here's how I'm going to do this. So let's draw ourselves a little table. All right. And so we had 3 of them that we identified: A, D, F, B, C, D, F, A, D, E, G, and B, C, D, E, G. And then we have our bolt holes. Which were subtracted, and then our stagger factors. Ahead of myself. Which are added. Then we have our net area. I'll give you a sec to draw this out. All right, has everybody got that drawing out? All right, okay, so watch this. So remind me with path ADF. How many bolts are we subtracting in path ADF? 1. And how many stagger factors? 0. So this is 1 and that's 0. So watch this. So we have our gross area minus one of these plus none of these. So what is the net area if I have the gross area minus one of these plus none of these? We'll say 2 decimal places. Is everybody following along? So the gross area minus 1 bolt hole plus 0 stagger factors. 11.13. Do I have a second on that? Now let's look at these two paths. How many bolt holes am I subtracting? 2. How many stagger factors? Okay, so this is 2, and that's 1. So help me out. The gross area minus 2 of these plus 1 of these. What is that?
10.41.
10.41. Do I have a second on that? Not too bad, right? And so the last one, help me out. How many bolt holes?
3,
And how many stagger factors?
2.
So 3 and 2. So 3 and 2. What's the net area?
9.69.
9.69. Do I have a second on that?
Yes.
Okay. All right. Now, so that's good, great, grand, and wonderful, but what's the answer? If I'm asking you what's the net area, which value would you use? Now keep in mind, the net area is used to determine the strength of the section.
Is it worst?
Use the worst case scenario. And so what's the worst case scenario? The 9.69. That's the answer. And so so first off, your net area answer is 9.69. And so if that doesn't make sense, think about it like this. Right? How many of you have ever eaten taffy before? Okay, if you've eaten taffy, sometimes you take the taffy like this. Sometimes it's kind of hard to actually rip that stuff apart, right? So imagine I gave you like a full thing of taffy, but I gave you just a tiny little strip. In other words, how does taffy look when it comes out of the packet? It's sort of like that. So let's say I gave you this one, or I gave another student like this one. And you both started ripping it. Which would be easier to break? This one, right? But why? It's the same material. Why is this easier to break? Because it has a smaller area. So it's the same thing here. If I take this steel member and I start yanking on it, and it wants to fracture, where is it going to fracture? It's going to fracture where there's the least steel available to resist that load. And that's along this path. Does that make sense? Everybody okay with that? Okay, I really want to make sure that's clear, because if you understand this, then the first problem on the homework is straightforward. Here's the problem, and what I did is, for this problem, so that we're all speaking the same language, I label everything. So everything's got the letters, but if you notice on future problems, there are none. So you sort of have to identify it yourself. So it's like this one is so that we can all speak the same language, but in future ones, y'all gotta figure it out on your own. Does that sound good? Okay, so this one, I'll go ahead and tell you, there are far more failure paths, okay, than what we just did. I think there's like 6 or 7 of them. And so the purpose of this problem is for you to identify them all. And so there's a pattern, and you'll start to notice that pattern pretty quickly, and you'll go, okay, I know what the answer is. And that's fine, but it's all about identifying those particular failure paths, okay? And so that's my first point. My second point is I will go ahead and tell you one hint. Let's say that you're looking at that path. Is it 1 stagger factor or 2? It's 2. Each of these is separate, okay? So keep that in mind. You can't use like that gauge and that S and compute a single stagger factor for the whole thing. No. Each of those are different. And it's because you've got this term squared, the math doesn't work out right. You have to treat each one separately, okay? So I'm just telling you that now so that you're aware of it. Everybody okay with that? Any questions? Yes, sir.
On the example we just did.
Yes.
Could you explain again why there was one like path that wasn't, like we wouldn't consider it as possible?
Oh, yeah. Okay. I will go ahead and show you why. It's a little weird, but I'll show you why, okay? So, here's the idea. This is the idea. And like I said, it's a little weird, so bear with me. Okay, how many bolts are in this connection? Just how many? 7, right? Okay, so to keep everything simple, would you agree that each bolt withstands 1/7 of the load? And I'll go ahead and tell you, it doesn't actually work out like that in reality. Anybody who's ever worked on like a lawnmower or done any sort of mechanical work knows that if you have a connection with a bunch of bolts, just some bolts are more engaged than others. That's just how it works. But for the sake of our discussion, it's close enough, okay? So let's say we're looking at path BC, EG, okay? So that's going to be the net area minus 2 holes, right? Somebody tell me what that is. I'm just curious. Yeah. We got an answer? 10.25, now a second. Okay. Okay, so that would be the path corresponding to 2 bolt holes. So right off the bat, it doesn't govern because we have one that's lower, right? But we're not done, and here's why, okay? Like I said, 1, 2, 3, 4, 5, 6, 7 bolts, right? Okay? If I fail along this path, one of the bolts has already fractured. Is that a fair statement? So here's the idea, okay? If you look at path ADF, what we would say is it corresponds to 100% of the load, and you'll see where I'm going. Path BC, EG, what we would say for this is that this path only corresponds to 6/7 of the load because one of the bolts has failed. Does that make sense? So we can't take this number and throw it in with these because we would be comparing apples to oranges. Each of these paths see all of the load. This path doesn't even see all of it. So if you wanted to do this for real, if you wanted to check that path, what you would have to do is take this and multiply it by that so that you're comparing apples to apples. So because this path doesn't correspond to all the load, you sort of have to adjust it so that it's apples to apples. So what is this? I'm just for the sake of discussion.
8.79.
No, other way around.
Oh.
11.95.
11.95. So that's more than any of these. So remember how I said that lead line paths don't govern? Yeah, they don't govern. Like never. And this is why. So like for instance, if you were checking like this path right here, well, it'd be the net area minus 1 hole, but you have to multiply it by 7/4 because 3 of the bolts would have failed. You see what I mean? It's a out there count, which is why I'm not making you do that at all. And it never governs, so that's why I usually don't worry about it. It's a little weird, so. But did that make sense? So that's why we don't worry about it. Does So far so good? Okay. Now, we did one that's a plate. Now we're going to do one that's a rolled shape. So we're going to look at the following staggered connection. This is a staggered connection along an angle. This one's a little weird. First off, that means we're going to need this, because everybody brought their AISC 15th edition steel construction manual, right? Yes, it's like, he won't call on me if I sit next to somebody that does, might not bring one.
Still call on me, but at least I'm
No, he was 100% prepared.
so I prepared for class stuff. So I didn't sit up there and jury.
You're going to do awesome in senior design. I'm messing with you. All right, so here we're dealing with a rolled shape, okay? This is an angle. We haven't discussed much the terminology behind angles, but there's not a lot to discuss. This is an L7 by 4 by 5/8. So whenever you're looking at angles that have unequal legs, you always denote the longest one first. So it's 7 by 4, the long leg is 7, the short leg is 4, and the 5/8 is the thickness of the plate, okay? Now, typically, what you do when you're dealing with angles is you always look up the area and you don't just compute it, because I have it drawn as these nice, pretty little rectangles, but in all actuality, they're really not. Like, if you look at the image, you've got these little fillets here, these little rounded sections, so it's not as pretty as just a set of rectangles, but this is just for my slide, so I probably should try and redraw that a little more accurately. Okay, now, we have a problem where we are determining the net area. Well, in order to determine the net area, the first step is to determine what? The gross area. So could somebody tell me what the gross area of an L7 by 4 by 5/8 is?
6.5 square inches.
6.5 square inches. That's quick. What page are you on?
1-44.
1-40 what? 44. Okay. So here's how I'll do this. I'll say 4 and L7. And that's table 1-7 on page 1-44. Now, I want everybody to be at the same spot, so I want to make sure everybody's able to find that value. Again, I know this seems simple, but part of the point of this class is to make sure that everybody's comfortable with the manual. That's the whole point. So I know it might seem silly that all we're doing is looking at numbers, but I mean, by the time we get to like week 8 and week 9, we're not going to have this like, okay, everybody, let's look it up together, because by then you'll be pretty familiar with this. So especially, you'll have homework assignments and things like that. Sound good? Okay. Since I don't think we really need to look this up, but what's the thickness going to be for this problem? 5/8. Yeah, it's 5. That's the whole point of the terminology. So, not necessary to look that up, but it's there. Okay. So we have the gross area. We have the goal is to determine the net area. Now over here, I'm going to adopt the same approach. We need the area of holes and we need the stagger factor. Okay? So let's look at the bolt holes. So the diameter of a bolt, is it 3/4 inches as well? I think so. So what's the hole diameter? Let's just keep this simple. 7/8. So the hole area is the diameter of the hole times the thickness, so 7/8 times 5/8, and so that equals. And like when you're doing your homework, I'm okay if you do this all in one calculation, like 3/4 plus an 8 times that. I mean, you don't have to follow this format just as long as you do it correctly and do it neatly. As long as you do it correctly, do it neatly, and use the right terminology, I don't care how you do it. So we'll say 3 decimal places for our purposes in here. The only reason in here, when I say like, okay, 2 decimal places to 3 decimal places, is usually because if you look at the example, that's enough specificity so that we know what number we're talking about. So, like if you just said 0.5 or something, well, it'd probably be good enough for design purposes, but then there'd be a bunch of 0.5s running around and we wouldn't know what value we were talking about. So 3 decimal places, what we got? Square inches. But in general, for net areas, 2 or 3 decimal places is fine, no more than that. You don't need to get any more specific than that. Okay. Now, this is where things get a little funky. And we're not going to finish this problem today, but I'm going to show you what we're going to do, and then we'll digest it. We'll tackle it on Friday. What is the S value? 2 inches, right. Okay. Now, does that matter whether or not I'm talking about this path or that path? No, the S value is always 2 inches, right? Now, the gauge distance, though, that one's a little unique, isn't it? What's the gauge distance here?
Exactly 3 inches.
3 inches, exactly right. What's the gauge distance here?
Is that the 1.5?
No, it's not. The 1.5 would be sort of from here to the edge. I'm looking for a gauge distance across here. That's a little weird. How do you do that? Because it's the staggers across the legs, right? That's a little strange. So, because it's a little strange, I am going to make it not strange. And how am I going to do that? I'm going to break out the samurai sword or lightsaber. And what I'm going to do is I'm going to take, I'm looking over here, I'm going to samurai sword or lightsaber through there, and I'm going to take this and stack it on top. And I'm going to turn this angle into a single plate. Okay? I'm actually going to perform some surgery to this this angle, if you would. So imagine, so let me do this. So imagine over here, what I'm doing is I've got my plate here. I've got this hole here, and so that's 1.5 inches. I've got this hole up here, which is 3 inches. All right? And then what I'm doing is I have samurai sworded that, and again, I'm taking this, and I'm sort of stacking it on top. So I've got that. I've got this hole here where that dimension is 1.5. Does everybody see what I did? Does that make sense? That I'm cutting that off and then stacking it on top. The reason why I did that is because I want to figure out what this gauge distance is. That's what I want to figure out. Does that make sense? Now, here's the $64,000 question. what is that distance? Make a guess.
11.
Okay, you said 11. What were you saying?
6 plus X.
No,
Distance is X.
no, you're probably thinking a little more complicated. No, you're saying it's 11. Now, you're saying it's 11 because that's 7 and that's 4, right? That is a very reasonable guess. It's wrong, but it's real close. Here's why. Over here, what is that dimension right there? I'll go ahead and tell you. This is 4 inches. But I didn't cut at the end. I cut and lifted that piece. So what's that dimension?
3 3/8.
It's 3 3/8, right? So this dimension is not 11 inches. It's 11 inches minus 5/8. Does that make sense? So this is 10 3/8. Now, if that's 10 3/8, now tell me what that is. Does that make sense? So now, if that's 10 3/8, and that's 1 1/2, 3, 1 1/2, what's that?
And 3/8.
4 3/8. Do I have a second on that? That's right. So we'll say 4.375. Okay, I know that was a little weird, but did that make sense? Yes.
So, why did you subtract 5/8 from that 4 distance to get?
Because, okay, this dimension here is 7. So from here, so you could say from here to that dashed line is 7. When I cut that nubbin off, stuck it up top. That width is not 4. That's 4 minus the thickness.
Okay, so would it be, to find that distance for other angles, would it just be the top length minus the thickness?
Yes. Yes. That's exactly right. That's a great question. Everybody else good with this? Don't worry, we're not done with this example. We're going to continue it on Friday. I just want to point out something really, really quickly before we close it, just to show you a shape of things to come. What we're doing right now is all about gross area and net area. I told you that when you take your first exam, there's 2 things that's going to confuse you. One of them is net area. The other is shear lag. Okay? Shear lag is something we haven't talked about yet, but we're definitely going to dive into on Friday. And in a nutshell, shear lag factors are basically trying to account for real-life behavior on a connection. When you look realistically at what the stresses look like along a connection, they're weird. They're not simple, okay? They're all over the place, okay? If you look, this is a finite element model of a tension member looking at the stresses as you yank on it. Out in the main body of the member, the stresses are nice and uniform. Like, see how it's all like yellow? It's all the same color. But when we're looking at the net section, we're not looking here, we're looking there. And the stresses are all sorts of weird right there along the connection. As a result, we can't ignore that, okay? That phenomenon, and we'll talk about why it's called what it is and how we handle it, but that phenomenon is called shear lag. The idea that the stresses are not uniform along the connection. And so we adjust that through the use of what's called a shear lag factor, okay? We're going to talk about shear lag factors on Friday, and once you have shear lag factors, we'll go through this in detail, but once you have shear lag factors and you have net area, boom, you've got tension members pretty much figured out, and we can start getting into full-blown examples, okay? Now, that is totally for Friday. We don't need to worry about that now. The only other thing I'll mention, and I'm going a couple minutes over, is that problems 2 and 3, you could probably determine the net areas of both of these problems right now, okay? So we've got gross area and net area for all of these, and you're halfway there for 2 and 3, and probably 1 you can finish right now. I'm sorry for keeping you a couple minutes over, but we don't have class on Wednesdays, so I figured that's fine. That's all I got, everybody. I need the sign-in sheet. If you have not turned in your homework, I need it now. I got to go. Catch a plane. We'll see you.